Good morning. We will start now. Let me share the screen. Okay, we'll start with a description of assembly language programming. I had introduced some instruction in the previous lecture, and we'll build over that to discuss how assembly language programming is done. We talked about machine language. This is something which is primitive as compared to the hardware to high-level languages like C, Java, and C++. It's designed to be understood by machine, so it has to be somewhat simple and primitive. Should be easily interpreted by hardware, and it actually provides programmer's view of hardware. So what programmer sees the machine is what is defined by the machine instructions. Programmer sees the behavior of machine in terms of what the set of instruction is and what they can do. While designing instructions or instruction set, one has to keep a few goals in mind. These should be designed such that you get maximum performance. So there's a question of efficiency. And at the same time, the hardware required to implement these instructions should not be very expensive. Okay, should not be very complex, and it should not consume too much of energy. At the same time, uh, when instruction set design project is being done, you want to do it in reasonable time. You can examine limited options and choose best out of that. So we of course are talking of one of the existing machines, and we'll try to familiarize ourselves with the language of that machine, namely ARM or Advanced RISC machine. So it's a popular processor which is used in many mobile devices and many small systems. What we have discussed so far are a few simple instructions. In the examples we considered, we talked about add instruction, subtract instruction. As you can see, these are doing some basic operations, so one addition at a time. And any complex expression has to be broken into a sequence of such operations. So add, subtract, multiply. So I could put these three together in terms of arithmetic instruction. And then we use move instruction just to move data from one register to other register. CMP is for comparison. LDR, STR are for moving data between registers in memory. There are other variations of load and store, LDR, STR, which deal with just 1 byte at a time, or half word, which means 2 bytes or 16 bits. Then to organize flow of control, we talked about branch instruction with certain condition checks. So branch on equal, branch not equal, branch on less than, and so on. And also plain branch without checking any condition. So it's also called unconditional branch. This is just a starting set of instructions, and as we uh, take more examples and discuss further, you'll see uh, more instruction. But this actually gives you some feel or some essence of what is there. So the instruction we have talked of do take care of simple control flow like if then else or loops. But one of the important features which most programming languages have is defining procedures as a function or creating procedural abstraction. That means you write code once and then you can use that at several points in your program. So you suppose you have a main program and then you have two procedures P and Q, which encapsulate some computation, some code. And main can invoke these procedures or functions at various points. So for example, let's say main is a sequence of statement. At some point you call P and then the function defined by P is done and you get back. You can call P again from some other point and get same thing done, of course, with different parameters possibly. Okay, so these procedures are usually made generic in the sense that you can specify some arguments or parameters over which they perform computation. Similarly, you could have calls and returns for Q. Now, to do that at assembly level or machine language level, what is required? First of all, you need an arrangement for control flow. That is, you should be able to call and should be able to return from procedure. So the control gets transferred from main to the procedure and back from procedure to the main. Also, you need data flow. That means there are parameters or arguments which need to be passed, okay, and results need to be brought back. Uh, apart from that, you need local and global storage allocation. That means the procedure should be able to look at some data structures which are local to it and different from what the main would do. So there is a question of storage allocation, which is exclusive for each procedure. Okay, there may be a need for something like that. And the procedures may not just stand alone. There may be nesting of procedures, and there could be even recursion. Okay, the procedure could call itself. So these two things complicate the matter a little bit, but we will see how we can do all this in a typical assembly language like what we are discussing now. So firstly,
Excuse me, sir.
control flow. Uh, Now, when a call is made to a function, what is important is that when you come back, you should come back and continue the same computation. Okay. So if there are two calls from two different places, the return must be to the corresponding following statements. Right. The instruction which you have in ARM is BL for this purpose, which is an abbreviation of branch and link. Okay, link is referring to the place where you are returning. Okay, so you are not simply branching, but you are remembering from where you are coming, and that information needs to be stored somewhere or remembered somewhere. Okay, so BL is a variation of branch instruction, but the additional job you need to do is to remember from where the call was made. So how do you return? The counterpart of return statement, which you see in typical C-like languages, is a move instruction. Okay, what we are saying here is move PC LR. LR is a register which is called link register, and this is the one which remembers where you have to return. Okay, moving that address into PC, which is the program counter, actually takes care of returning. All right, so when you say BL, the return address is saved in this register called LR or link register. And for returning, you simply transfer that into PC, and now PC or the program counter is pointing to the address where you need to go back. Okay, so this is the return control transfer. Let me check if you have any questions at this stage. Are there any questions?
Hello, sir.
Yeah.
Sir, when you said that when we are calling function, suppose we are calling the function f from instruction, suppose 1,
Yeah.
then after calling it, we should return the next instruction after the x, not from after the f, right? Like
Yeah,
that.
yeah. You need to return to the next instruction.
Okay. Okay, sir.
Yeah. You need to return to the next instruction, and that is the address which will be stored.
Okay, sir.
Sir, can you repeat what like move PCLR statement would do?
Okay. So first let's go back and understand what BL is doing. BL is like branch instruction. Okay. Unconditional branch in this case, which means the PC changes to the specified address. So now when you are saying BL func, this function, this label uh, is corresponding to some address. What we see in assembly language is a label. What we see as a counterpart in machine language is an address. Okay, so you're branching to this address. And second thing you're doing is that the address of the next instruction is stored in the link register. Okay, this is part of the BL instruction. And when you move the contents of LR into PC, then automatically the program starts execution from the address which is there in PC, and that will be the instruction following X. So I hope that is clear.
Yes, sir. Thank you.
Okay, so now these registers I have just talked of, PC and LR, are actually part of the register file. So the register file in ARM has 16 registers which can be called, which are labeled as R0 to R15, but some of these have additional names because of their special functionality. Okay, so R15 is actually nothing but program counter. So program counter is not a separate register, but R15 acts as program counter. R14 acts as link register. And in the same breath, I'm mentioning R13 also, which acts as stack pointer, because there are certain things which require use of stack. So R13 acts as stack pointer. Now, this is something which is specific to ARM. There are other processors where these registers would be separate. They will not be part of the main register file. Uh, the one use of keeping these registers as part of register file is that you could, for example, use instruction like move PCLR. Okay, so this is not a different move instruction. Uh, you can say move R1 comma R2, or any you can move from any register to any register. So same instruction is good enough to transfer contents of LR to PC. If PC and LR were separate register, then you will require special instruction. The usual instruction which moves from one register of the register file to other register of the register file, that will not work for PC and LR if they were different. Okay, but uh, one could argue that, out of 16 register you are losing out 3 for this special purpose, and actually only remaining 13 are general purpose register in true sense. Okay, yeah, so that is true. That's the downside, but the upside is that the instructions which are applicable to general registers are applicable to these special registers also. So it's a debatable point, do you have plus and minus? Okay, so here it shows the picture that in main you have BL instruction where call is occurring, and at the end of the procedures or functions, you have this move PCLR instructions. Now, the question comes up is how do you have nested call? Suppose P were to call Q, okay, then if we have a BL instruction within P, then contents of LR would be lost. Okay, so you won't be able to return back to the point from where P was called. But there are ways of handling it. We'll look at it shortly. And recursive call also poses similar problem. But before we do that, let's look at how parameters are passed. So one method of passing parameters is to use registers. And this picture illustrates. So I'm using the terms caller and callee. Caller is the part of the program which is making a call. Callee is the part of the program which is being called. So in the caller, let's say here is the call, BL to callee. Now, before you do that, you would move the parameters into some registers. And within callee, you can get the parameter, you can access the parameters from those registers. Okay, I'm talking of think in terms of some information going as input parameters and some results coming out as output parameters. So what information needs to be sent to callee is put in appropriate registers, and callee understand in which register you will have parameters, and those parameters can be picked up here and computation performed. Similarly, the result could be put back in some register, and the caller would pick up the results from those registers after return happens. Okay, so that's one mechanism. Uh, the other mechanism is through stack. So you create a stack and before calling, push parameters into the stack. The callee can pick up information from the stack, put the result back on the stack, and caller can pop the results when return is made. Okay, so stack is also a convenient mechanism. Of course, it is faster to work with registers uh, than with stack, which is part of the memory. Now, there are some conventions which are followed where we sort of combine these two. You may have multiple parameters. If you have a complex procedure, there are many parameters you may be passing. So the convention is to pass first four parameters through registers R0, R1, R2, R3. Okay, so this is just a convention. The hardware does not enforce it. It's up to the programmer. The idea of such convention is that a large program may be written by multiple programmers. So caller is written by one programmer, callee is written by another programmer, and these conventions will help them in coordinating. Okay, so first four parameters get passed through these registers, and the result comes back in R0. Beyond this, I mean, if you have more values going into the callee and more results coming out, use stack. Also, the callee can destroy these registers R0, R1, R2, R3, and one more is kept in this list, R12. That means the contents of these can be modified because callee will also require some registers for its own computation. And uh, once you have picked up the values from here, you can, in the callee, you can change the value. You can use it for some other purpose. But callee is not supposed to destroy other registers. Now, in case callee has to use more registers than these, then it has to first preserve their contents. By that we mean you save it into memory. Uh, Except PC, of course, PC keeps changing automatically. And on the other hand, caller cannot assume that the value it is putting in R0, R1, R2, R3, and R12 will be preserved. So it should take care of preserving it. If it needs those values after the call, it should preserve. Okay. So this way, responsibility of preserving or saving the contents of register is divided. So that is part of the convention. The caller preserves these registers and callee would preserve other registers. So with this additional responsibility, how does the picture look like? So we had this picture where before calling, parameters are moved into registers, and after return, the results are picked up from registers. Okay. And within callee, you are accessing parameters which are in the register and putting result back in the register. Now, the responsibility of saving register has been defined in the convention. Caller will save the values it needs to preserve across the call. Okay, so R0 to R3 and R12, if those values are required, they need to be saved and restored. On the other hand, the registers other than R0 to R3 and R12, if any registers are to be modified, their old contents must be saved right in the beginning and they can be restored at the end. So even when compiler would generate the code for ARM assembly, it would follow this convention. Okay, because you may be compiling different parts at different times and then putting them together, link them together. So certain conventions are always helpful. Any question about this?
So can you tell how the saving part is done?
Okay, saving at the moment, let's understand saving means uh, storing the contents in some memory location. Okay, restoring means from getting back from memory to the registers. Now, where in memory, it could be a fixed location or it could be stack. Okay, saving could simply mean that you push in the stack. Restoring means you pop from the stack. So as you can see that, okay, we will be coming to that. So when you have nested and recursive calls, then the saving restoring is best done on the stack.
Sir, so the stack is present in the memory, right?
Yeah, there is no fixed stack as such. In memory, anywhere you can create. So you initialize stack pointer to some memory location, and then stack starts building from that point onward.
Okay.
So there is no uh, hardware stack, so to say. The programmer has to manage a stack in the memory itself. Okay, now so let's look at an example where we will be using a function and function call. Suppose you want to compute GCD of n numbers, right? And these n numbers are stored in an array. We call that array as A. So initialize G to the first element of the array and then iterate through this loop with I going from 1 to n minus 1. Okay, all you need to do is take the current value of G and the next element find the GCD. Okay, that value will be used again in the next iteration and so on. So you keep iterating over this for all the values. Now you can see similarity with the sum of n numbers we had. We had sum which could be initialized to a0 or we initialize to 0 depending upon whether you iterate from 0 to n minus 1 or 1 to n minus 1. And then in the loop we have this operation done. So we have already written a program for summing n numbers. We'll modify it slightly to perform GCD of n numbers. So this was the array sum program. L is the beginning of the loop, and this BLTL. So this part is the loop. All right, from this LDR instruction all the way up to BLT. So here it's a transfer back, and here is the initialization part. You are initializing the running sum to 0, loading the address AA into R3, and the final address, the last address you're going to take is computed here by adding 400 to R3. So corresponding to 100 elements, each occupying 4 bytes. We have the final address as the initial address plus 400. Okay. So it is actually we have the elements A0 to AN minus 1, and this address we have calculated is the first address after the last element of the array. Okay. Our check here is BLT, branch if less than. So as long as it is less than, we keep doing it. As long as the address is less than R6, to compare R3 with R6 and loop back if R3 is less than R6. Now, a few things have been added in the beginning and in the end, and I briefly explained. Let me just repeat that. All these dot statements are basically assembler directives. They are not executable statements. They are not instructions. They are simply commands or pieces of information given to the assembler. So dot text indicates starting of the code and dot data indicates starting of the data space. Okay. Dot space is a way to reserve space for some array, for example. So we are reserving 400 bytes for AA, and dot end marks end of the program. Dot EQU is equating a symbol, which is SWI exit in this case, with a number. So 1 1. 0x stands for 0x indicates that it's a number in hexadecimal. And we have this SWI instruction. So this is actually an instruction which causes the program to halt. And halting means that when you are simulating this program, the control goes back to the simulator. So I'll come to SWI instruction in a short time. This is used also for input output. Now what we want to do is primarily replace this main body of the loop, which is adding R5 or the next array element to the running sum. So instead of that, we'll put something of this kind. R1 gets GCD of R1 and R5. Okay. And for doing this, we'll make a call. So eventually we'll have a BL instruction, but we'll see how we get to that. This is where we primarily want to make the change. The initialization will also change somewhat. So instead of initializing R1 to 0, that running sum to 0, we want R1 to have the first element. Okay. So therefore, first we are initializing R3 to the address, starting address of the array. And we have also prepared the last address. And here in this third instruction, we are loading into R1 the first element of the array. So R3 with 0 offset. Okay, R3 is the starting address with 0 offset. You pick up the first element and put in R1. And since we have already looked at the first element, we increment R3 by 4. So that now points to the second element. The iteration will start from second element onwards. All right, so the initialization is slightly modified. Okay, initialization of R3 and R6 is exactly same, but initialization of R1 is modified and R3 is updated accordingly. Okay, so now let's leave those dot assembly commands aside and focus on this part. So how do we implement R1 gets GCD R1 R5? So a call has to be made. But before that, let's modify this program. Let's change the registers so that the conventions which I mentioned are followed. Okay. We like to pass the parameters in R0 and R1 as per the convention. Actually, the program could still work if you use R4, R1 and R5. It can still work. Hardware will not complain. But just I'm trying to show you, if you were to follow convention, how will we use the registers? So we'll eventually say something like this: R0 gets GCD of R0 R1. The two arguments are being passed in these registers. The result is put back in R0. All right, and we make this change in the register all through. Right. Also, let's leave aside R3. Let's not use R3 here because R3 is also used for passing arguments and it's not preserved across this. Whereas we want R3 value to be preserved across this call. Okay. Now, at this point, we don't know what GCD is going to do, how many registers it is going to use, what it is going to do with R3. So let's not use R3. We replace it with R4. And now we are safe. Okay. If GCD has to use R4 also, it will have to take care of preserving it and restoring it. So we don't need to worry about it. All right, we can safely write program in this manner. Having done that, you notice that R0 and R1 are already set up. R0 is containing the running value of GCD. R1 is containing the pointer to the next array element. And we can simply just say BL GCD. GCD is the starting address of the GCD function. Now let's go to the GCD function. So it's very straightforward. Compare R0, R1. If they are equal, then we are done. So BEQ2, label RET where we will make the return. Otherwise, you subtract. You'll see that there are two labels here: subtract 0, 1 and subtract 1, 0, which I'm using to say that here we will subtract from R0, we'll subtract R1, and here from R1 we'll subtract R0. So subtract R0, R0, R1, and go to the beginning, or if it is, so you are coming here if less than condition is not true. Okay, we compared R0 with R1. If R0 is less, then we are coming to sub 1, 0. Okay, where R0 is subtracted from R1. So smaller one is subtracted from the larger one. All right. Otherwise, the R1 is smaller and that is subtracted from the larger one. And in any case, we come to we branch back to GCD and come out of this loop when the two become equal. Okay. At that point, we want to go back. So simply say move PC, comma LR. So this is the GCD function. So let me see if it is clear or there are any questions.
So once could you explain the last statement, move PC, LR?
Move PC, comma LR is moving contents of LR into PC. Okay, and that causes program to jump to the new location. So PC always points to the instruction which is to be executed. The processor hardware looks at PC, takes that address, gets one instruction from memory, executes. And while executing, PC moves to the next instruction. So the next instruction is fetched, executed, and PC moves to the next instruction. So when a jump is occurring, when you say branch to some location, what will happen in BLT is that if the condition for R0 less than R1 was true, PC will get this value. Okay. The label sub10 has some address. That address gets transferred to PC. So by changing the contents of PC, you're branching or jumping to some appropriate location in the program.
Hello, sir.
Yeah.
So, sir, every time PC is taking a new value, that is a new instruction, either BLT or either sub 01 or 10. So, sir, finally, what is happening as you say that move IR to PC?
Move LR. This is small l. So in this particular font, it is appearing as capital I, but this LR. LR stands for link register. Link register is containing the address where we need to return. So we made a call from this point. Okay, this BL instruction will cause the address of next instruction to be saved in LR. So move PCLR, you can read this as branch to the address which is contained in, which is saved in LR. Okay. So when you move something to PC, basically you are branching to some location, some address.
Okay, sir.
So I have a doubt on the previous slide.
Yeah.
So over here, we replaced R3 with R4, right? Because R3 can be destroyed by the program which it calls. But doesn't this thing first save the contents of R3 and then do the BL and then again restore it? So it shouldn't be a problem, right?
We could have done that if you were using R3. We could have continued to use R3, and before doing BL, we could have saved it, and after return we restore it. But here I've avoided. So I mean, there may be situations when you need too many registers. So you will be forced to save and restore. Okay. If that was the case, if you're constrained to use R3, or if you choose to use R3, then all you need to do is save it before call and restore it after the call.
So will there be additional commands for saving and restoring?
Yeah. Yeah. For saving, you need to use str. For restoring, you use LDR.
Okay. Okay. Thank you.
Later on, we'll also talk of instructions which can save multiple registers. Okay, so you may have many registers to be saved. So instead of saying str for each of these, there is a command store multiple. Okay, multiple registers could be saved in one instruction, and similarly multiple registers can be restored.
So like we have instructions like VE, VLT, and all these. So like, do they also internally have something like move PC to some location or register?
Yeah, effectively, they are moving some address to PC.
Okay, sir.
Yeah. Uh, the difference here is that these branch instructions, you are branching to a fixed address. So when you say, let's look at this. Okay, BLTL. So L is a constant here. L is this specific address. L is an address. We are seeing it only as a label, but assembler will assign a fixed address to L. Okay, when this program is converted to machine language, these instructions each will be provided some address, and there will be some specific address for this instruction, that is L. So in branch instruction, the address part is fixed. In a way, move allows you to branch to a variable address which you don't know a priori. When you write GCD function, okay, you don't know where you are going to return. It is known only when the program is running. From where the call comes, you need to return there. So therefore, move is a way. Some now imagine a processor where LR and PC were not part of the register file. They were dedicated registers. There you would need specific instruction. So in fact, some processors have instruction called return. It's just called return, and from the dedicated register, which is link register, the address is transferred to PC. Okay. Some processor use instruction like branch on register. Okay, instead of branching to a fixed address, you branch to an address which is provided by a register. Now, contents of registers are not known when you are writing the program. So, branching to a variable address is what is required. Okay, any more question? Okay, so now let's look at the broader picture about the instruction. All these instructions which perform arithmetic or logical operations or data processing in some way, these are categorized as DP or data processing instruction. They form one category of instruction which are represented in similar manner. Okay, so it includes arithmetic instructions, logical instructions, which operate on two operands and have one destination. So there is one destination, two operands, OP1, OP2. Move instruction have one partless. You specify one destination and one source. Then there are compare and test instructions where you have no destination but two operands. We have seen example of that. When you compare two registers, we are not putting the result specifically in another register. So where does the result go? Result goes to set or reset certain flags. I'll describe what this means. But the result is not going to one of those 16 registers. A similar instruction is test instruction, uh, which also takes two operands, performs some logical operation, and the result is put in flags. So to begin with, let's look at arithmetic instruction. We have seen to add and subtract. Okay, you notice that I'm not talking about multiply here because that's a slightly different instruction. Multiply and divide are somewhat different, so we'll talk of them separately. Here we have add and subtract, and there is also what is called reverse subtract. Subtract does OP1 minus OP2, and this does OP2 minus OP1. Okay, because add is commutative, so we don't need reverse add. It will be same thing, but for subtract there is an instruction provided which does reverse subtraction. So you might wonder, why do we still need it? You can always in the instruction itself change the operands. The answer is that uh, operand 1 is always a register, but operand 2 could be register or a constant. So therefore this makes sense. Apart from these three instructions, we have variants which include carry. Okay, so ADC is add with carry, SPC is subtract with carry, RSC is reverse subtract with carry. What it means is that ADC will what it will do is OP1 plus OP2 plus carry. So there is a flag called carry flag. I mentioned about flags. Carry is one of the flags, and there are some other flags. So this will be useful when you are, for example, trying to perform addition of two 64-bit numbers. But basic instruction does only 32-bit addition. So when you perform addition of two, you first add the lower halves. Okay, lower 32 bits, and you may get a 0 carry or a 1 carry. Then you perform addition of the upper 32 bits with carry. Okay, so carry coming from 32nd position has to go to 33rd position. That is where you could use instruction like add carry. The DP instructions include logical operation. There are 4 of these: and, or, exclusive or, and bit clear. So these are very obvious: bit by bit logical operation, and, or, XOR. Bit clear basically performs OP1 and complement of OP2. So wherever you have a 1 in OP2, that corresponding bit in OP1 gets cleared, is made 0, and that you can see for yourself by analyzing this operation. Okay, so you basically, if you have a bit pattern in OP1 and you want to clear certain bits, you have ones in those positions in OP2 and perform BIC operation. There are two move instructions: move and move negated. Okay, MVN basically moves complement of the source to destination, bit by bit complement. So you can see that these 4 operations, these 4 instructions require 2 operands. So complement or not is not fitting into this, and that is clubbed with the move operation. So by the way, source and destination could be same. So basically you'll take contents of a register, complement, and put it back. In some sense, move is a misnomer. Normally when you are editing, you moving would mean that you take something and place it elsewhere, but here actually it would have been more correct to call it copy. When you are using move instruction, the contents of source register are copied to destination register. Okay, the original source remains unchanged. There are 2 comparison instructions: normal compare, which basically performs subtraction, and then the subtraction causes some flags to change. I'll come to that shortly. And compare negative is comparing OP1 with minus OP2, or you could basically see that OP1, it performs OP1 plus OP2. The sum is not saved, but it is used to set or reset flags. Test instructions are like comparison. They perform these logical operations. The result of AND or exclusive OR is not stored, but only used to effect the flags. Okay, this is test, and TEQ is test for equality. So you'll use TST to test which bit, if there are bits, particular bits which are set or not. Okay, perform AND operation. This performs exclusive OR operation. Let me jump a little ahead and at least show you the flags which are there. Yeah. So I'll go back to instruction, but I've been talking of flag. Let me mention the flag. So a carry flag, I've already mentioned. When you perform arithmetic, a carry may result that is saved in C. So think of these as 4 flip-flops or four bits which are part of a bigger register called status register. Okay. So we will not talk much about that entire register right now. It has many other bits, but 4 bits of concern right now are these 4. So carry flag, B is the overflow flag, which indicates that previous arithmetic instruction resulted in overflow. If the result of arithmetic is 0, arithmetic or logical operation 0, then Z flag is set. If the result is negative, then N flag is set. So when you're comparing, for example, the flags will get changed in some way. Okay, and then you can test these flags using branch instructions. So I'll come back to branch instructions again, and let's so compare and test instructions. Their purpose is to modify the flags and test them later on. Now, so DP was one category. Let me complete the instruction categories first now. DP was one category. We have seen arithmetic, logical, move, and compare. These 4 categories, compare and test instruction. So 4 categories were there, subcategories. The next major category is DT, which stands for data transfer. We have already talked about this: LDR, STR, LDRB, STRB. These are for byte. LDRH, STRH for half word. A variant of these two LDRs, LDR byte and LDR half word, are LDR-SB and LDR-SH. Load register signed byte and load register signed half word. So when you are filling only a byte or half word of a register from memory, you need to fill up rest of it with something. So either you fill those with zeros. Okay, if you are loading a byte only in a register, the remaining 3 bytes can be filled with 0. That's what will happen in LDRB and LDRH. But in these cases, the sign bit gets extended. So if you have loaded 8 bits, which is a negative number in 2's complement form, the leftmost bit will be 1, and then the bytes which are unloaded, which are not being loaded now, will be filled with that sign bit. Okay, so this is called sign extension. Uh, so if you're treating the byte or half word being loaded just as a logical quantity, you can just fill 0 in the remaining part. But if you want to look at that as a signed number, signed integer, then you do sign extension. So here is the instruction or the pair of instructions which perform loading storing of multiple registers. So LDM STM stands for load multiple, store multiple. Any subset of registers can be specified here, uh, either for loading or storing. So we'll not go into details of how you do that. We'll see later. But right now, just note that such an instruction is available. Now let's look at comparison and elaborate a little bit further. After comparison, you can use branch with different type of conditions specified: BEQ, BNE, BGE, and so on. All the 6 possibilities are indicated here. This is if the comparison was done of signed numbers. If you're dealing with unsigned number, then there is a slight variation which has to be done. Of course, test comparison for equality and inequality. This is independent of sign. Okay. If 2 numbers are equal, they are equal. It doesn't matter whether they are signed or unsigned. But comparison for less or greater changes. Okay, because the range of signed number and range of unsigned number is different. All right, and you're doing this comparison by performing subtraction. So the meaning of overflow is different in the 2 cases. So for unsigned, there are different instructions. Counterpart of BGE is BHS, which stands for branch if higher or same. Similar meaning, but just to keep it different, a different name is given. Instead of less than, you call it branch if lower, greater than, branch if higher, and this is branch if lower or same. Now internally, what happens is that these instructions are doing nothing but testing these flags in some manner. Okay, uh, by looking at these flags, you determine whether it is less or greater, less than equal, higher, lower, higher or same, and so on. All conditions could be. All these conditions are basically checked by looking at these flags, and this is the table that will define the relationship. Uh, branch on equal will basically check if Z is 1. Uh, ignore this first digit which is appearing here. Just look at this. Equal means Z is 1. Not equal means Z is 0. Okay, why it is so? When you are comparing, basically you are subtracting, you're doing OP1 minus OP2. Okay, if the 2 numbers were equal, if OP1 was equal to OP2, the result would be 0 and flag Z would be set. Okay, so Z equal to 1 means that comparison done before this, the result of comparison is equal. Uh, carry being set is an indication of higher or same of unsigned numbers. and carry being 0 is opposite of that, which is lower. That OP1 is lower than OP2. If OP1 is lower than OP2, C will be 0. If OP1 is higher or same, then C will be 1. Why? Because subtraction is being done actually by taking 2's complement of OP2 and getting added. Okay. So what will happen? Just do this mental exercise. Suppose you take a number and add 2's complement to it. What will you get? What will you get as sum? What will you get as carry? So can you see that 2's complement, suppose x is a number, 2's complement of x is nothing but 2 raised to power n minus x. And when you add these two, you get 2 raised to power n. And 2 raised to power n would show up as a final carry and all zeros for the sum. Okay.
Yes, sir.
Yes, sir.
So
Sir,
okay,
so
now yeah.
HS is
Question.
implemented as sum of the as the sum of the operand and its complement.
Yeah, subtraction is implemented by adding 2's complement. So although I said OP1 minus OP2 is performed, what we are actually doing is OP1 plus 2's complement of OP2. Okay, so let us say you want to do x minus y. So what you will do is x plus 2 raised to power n minus y. Sorry, yeah, 2 raised to power n minus y. And if x is higher than y, if x is more than y, the result will be more than 2 raised to power n. Okay, so there'll be a carry and there'll be some non-zero sum. Therefore, if OP1 is greater than equal to OP2, interpreted as unsigned numbers, then carry will become 1. Okay, otherwise carry will be 0. So there are, apart from these branch instructions which I have listed here, there are some more branch instructions which are being shown here. There is BCS, which is branch if carry is set, and there is BCC, which means branch if carry is clear. So these two have exactly same meaning. BHS and BCS are same. BLO and BCC are same. Okay. Next we have BMI and BPL. BMI is branch if minus, BPL is branch if plus. So these instructions are simply testing n flag. If the result is positive or negative. Okay, n is the sign bit of the result. Next two are testing V flag or the overflow flag. BVS is branch if V is set, BVC is branch if V is clear. So we have looked at these 8 conditions which are testing these 4 flags one way or the other. Now there are, yeah, question.
So what is the meaning of V set or V clear?
V is the overflow bit. Okay, so if you are adding 2 numbers and interpreting them as signed numbers, the overflow is not given by carry. Overflow is there if the last 2 carries are different. If last 2 carries are same, there is no overflow. Okay. Maybe if you have forgotten 2's complement arithmetic, we can maybe discuss that separately. But this condition of overflow is different from carry. So actually for unsigned number, C itself indicates overflow. But for signed number, the condition is a little different, and another flag V indicates overflow. So BVS and BVC check whether V is set or clear. Now, apart from these, there are instructions which check a little more complex conditions. So branch if higher, you notice here HS means branch if higher or same. Here we are checking just for greater, okay, not greater than equal to, but greater. Greater for unconditional, for unsigned numbers. So if C is 1 and Z is 0, that means that equal condition is being excluded. So if Z is 0, that means the result is not 0. And strictly speaking, OP1 is greater than OP2 in unsigned interpretation. Complementary of that is lower or same, less than equal to, where C is 0 or Z is 1. Okay, Z is 1 indicates equality, and this indicates less. So lower or same. These are signed greater than equal to and less than. So this condition, it may not be very obvious to begin with. Condition n equal to V is a condition for greater than equal to of signed numbers, and its complementary one is less than. So let's understand these. Suppose to begin with, let's assume that V is 0. There is no overflow. Okay, you have performed a subtraction of signed numbers. There is no overflow, and sign is 0. Okay, we assume V is 0. So if n is 0, then it indicates greater than equal to condition. All right. No overflow and not negative. Okay, so that means greater than equal. On the other hand, if V is 1, that means overflow has occurred. Then this condition, you see, when overflow occurs, then the sign of the result becomes opposite. Okay, if V is 1 and n is 1, it will indicate the same condition, that OP1 is greater than equal to OP2. GT and LE, in GT we exclude Z equal to 0 condition. Sorry, Z equal to 1 condition. So we insist on Z being 0. That means the two are not equal. So it is strictly greater. Okay, it is same conditions, but we bring in Z also. Here we are excluding the case when the two are equal by insisting that Z is 0. And here we are saying this, either this or this. So Z equal to 1, which means the result is either result is 0 or it corresponds to less than. So less than equal to means either less or 0. And lastly, we have BAL, which means branch always. Okay, that means ignore the flags and just do unconditional branch, which is same as saying B, but if you say BAL, it would mean the same thing. Okay, here is a summary of some assembler directives. Again, there's a much larger number, but I'm just showing some we have seen and some which are somewhat similar. So dot text, dot data indicate beginning of code part and data part. Dot and indicates end of the program. Dot EQ equates a symbol to a value. Dot space reserves some space. Dot word would also reserve some space, but also initialize that space. So you could specify a sequence of words which will get initialized in the data area. So you could initialize by giving a sequence of words or sequence of bytes, or initialize some strings. So we will see examples of these shortly. Now, before closing, last thing let me do is describe some input-output operation in ARM. For this, there is an instruction called SWI, which stands for software interrupt, that is used. So these software interrupts are used generally to invoke some service provided by system software. So making system calls to the operating system. In ARM sim, the simulator you are going to use to simulate ARM programs, these SWI instructions are used to perform input-output from or to standard input or standard output, which are basically the console provided during the simulation, and also input output to the file. So also it supports opening closing of the file. So you can define a text file, for example, and read that in the simulator, or you could if you're producing some result, you can save it in a file. So all that is done through SWI instruction. And one example of SWI we saw was halt execution. There are many more, but we'll just talk of these. Now, depending upon which ARM version, which ARM sim version you use, there is some variation in the way this IO is done. Here I'm showing for an older version, 1.91. What you will see now is 2.01. So I'll come to that. So SWI instruction actually takes some parameter, some code, which could distinguish different SWI instruction. So different instructions could be used for different purpose. And in this version of ARM simulator, this specifies different IO operations. So for example, code 02 means that you are writing on standard output channel. Okay, that means whatever you want to write will be displayed on the screen, not going to a file. So this instruction requires R0 to be loaded with an address where the information you want to display is stored. So I'm showing at the bottom, you see message is a label. That means somewhere in the data section you will write this. And this directive means that you initialize the data area with this string. Okay. So before SWI 02, you load R0 with this address. Okay, so ASCII Z means a null terminate string. So it will print the entire string, and when null is encountered, it will stop. So the sequence of characters up to null are going to be displayed. There are similar codes for performing input, opening file, closing file, performing input output with the files, and one code was for halting the program, as we had seen. It's done slightly differently in the current version of ARM. So let me bring your attention to this SWI here. So instead of giving different codes, it has fixed one specific code, 1, 2, 3, 4, 5, 6. Okay, these are 6 hexadecimal digits. So it's a 24-bit number you are specifying here. So all IO operations are actually unified into a single SWI call. And what distinguishes different operations is the content of R0. So before this, you put appropriate code in R0. So in this case, I want to do exactly same thing. And 5 is the code for write. So you don't need to remember these codes and so on. In the documentation, it will be available to you. I just want to give you a feel of how it is done. So this SWI will require R0 to contain code of the operation which you want to do, and R1 to point to an area where other parameters are kept. Okay, so we have initialized R1 to this address where 3 spaces are reserved, initialized to 0, but they are getting filled up here in this part of the code. Okay, what you will notice here is that we are storing something at address given by R1, then we are storing something at address given by R1 plus 4, and then something at address R1 plus 8. So 3 locations which were initialized to 0 here are being filled up here. The first one is indicating, you can see that we are loading one in R4 and storing it in this address given by R1. Okay, so the first word is filled up with code 1, which is indicating where are we going to write. So we are ultimately performing a write operation, and this number 1 means it is standard output. Okay, how do you work with files? I think we'll discuss sometime later, but here I'm just indicating how to write on standard output. Okay, the second word is filled with address where information to be displayed or written is stored. And third one is giving number of bytes. So in this case, there are 8 characters. So I'm not terminating it in 0. I know that there are 8 characters. So this is the third parameter. Okay. Once I initialize these 3 parameters in this memory area, and R0, R1 have the right value, I can give a SWI call. So it may look a little cumbersome, but that's how it is. So just a few words about what actually are these software interrupts. There are other terms used for these: system calls, traps, exceptions, so on. These are software interrupts. So you might ask a question, are they hardware interrupts? Yes, hardware interrupts are caused by events conditions which are detected by hardware. They could be intentional, for example, IO event, or unintentional like hardware fault, power outage, arithmetic overflow, etc. So the key thing is that the response to interrupts, whether it is caused by hardware or software, is of similar. The mechanism is same, and the response is simply execution of some predefined code. That code is called interrupt handler or interrupt service routine, or ISR. So how is ISR different from normal subroutine or procedure? Normal subroutine or procedure is invoked by BL or call instruction. Okay. ISR gets invoked by SWI or some hardware condition. And why do we distinguish between these two? So for security reason, processors have 2 or more modes. Most simple case is that you have a normal mode or user mode, and you have a privilege mode or kernel mode or supervisor mode. Okay, there are some things which can only be done in privilege mode, not in normal mode. So the application program executes in user mode. To do certain privileged tasks, execution of some kernel code is required. And that code is invoked through software interrupt. Okay. So that's all for the moment. Let me just announce that I have put a link on Moodle, which will take you to the place from where you can download ARMSIM simulator and install. So please follow the instruction. And then there is a little question you need to answer, confirming that you have done it. Okay, so you download and then try to run this array sum and GCD example and confirm that you have done it. Okay, so I want that infrastructure to be all ready for you. Now somebody had asked me a question whether ARMSIM runs on Linux on Mac or not. So it does not directly run on Mac. Earlier version there was a way of doing it, but now there is a little more complicated way of doing it. You need to either use boot camp or run a virtual machine and then you do it. So instructions are available if you go to the website, which is for which link is given. Okay, so please do that. It needs to be done within the next 2 days, and you need to confirm that. All right. Any question finally?
So
Sir, the installation.
Yeah.
Sir, the installation doesn't seem to work. The link you
link doesn't work.
I mean, the link works, but when I install the MSI file, I execute the program, but I do not see where is ARM installed in Windows.
Okay, so you send me a mail. I'll ask some TAs to look into that. Okay, anybody who's having problem in this, please send me mail giving details of what actually you're doing and what you're observing. So we'll help you out. Okay. Yeah.
So when will the registration issue be solved?
I have been after them, so probably mails have not worked. I'll have to make call and ensure that you guys are registered. So as of now, I think all those who have made requests to me can be accommodated. There is no issue from my side, and I'll try to make sure that it happens. Okay.
Right.
Today's, I know tomorrow is the last date, so I'll push it through.
Thank you, sir.
Okay.